Imagine this. You are standing on the surface of another world. The sky above you is not blue, it is pink. The sun is a pale disk, half the size you remember. The ground beneath your feet is red. Red as rust, red as blood, red as the color of war, which is why the Romans named this planet after their god of battle. You turn to look at Earth. You cannot see it. From here, Earth is just a point of light in a sky filled with stars. Everything you have ever known, every person, every place, every moment of your life is contained in that tiny speck of light. And you are alone, truly, utterly alone. The nearest other human is millions of miles away. The nearest hospital is on another planet. The nearest breath of fresh air is a dream. This is Mars, the red planet, the dream of generations, the next great frontier. But here is the thing about Mars. It does not want you here. The moment you step onto its surface, it will try to kill you. The air is poison, the cold is lethal, the radiation will shred your DNA, the dust will fill your lungs, the weak gravity will steal your strength. Everything about Mars is designed to end human life. So why go? Why would anyone leave the safety of Earth to risk death on a frozen desert planet? Because Mars is the challenge. It is the frontier. It is where our future lies, if we can figure out how to survive. For centuries, we have dreamed of this moment. For centuries, writers have imagined Martians and explorers. Scientists have scanned the red surface for signs of water, of life, of anything that might tell us we are not alone. And now, for the first time in human history, we are actually planning to go. NASA wants to send humans to Mars in the 2030s. SpaceX wants to build a city there. The dream is no longer science fiction. It is engineering. It is physics. It is the hardest thing we have ever attempted. This is the story of how we might survive on Mars, the dangers we face, the solutions we have imagined, the science that will get us there and keep us alive. Settle in by the fire. It is a long journey. This is Mars, why we cannot survive and how we might. Mars has been watching us for as long as we have been watching it. To the ancient Egyptians, it was Har-Detcher, the Red One. They tracked its movements across the night sky with the same precision they applied to the Nile's floods. They saw its red color and associated it with Set, the god of chaos and violence. To the Babylonians, it was Nergal, the god of war and destruction. They recorded its motions on clay tablets, noting when it appeared bright and when it dimmed. They believed that when Nergal shone brightly, war was coming. The Greeks called it Ares, after their own god of bloodshed. The Romans renamed it Mars, the father of Romulus and Remus, the god who gave his name to the month of March, when armies marched to war. They saw the red color and imagined war. They saw its erratic movement across the sky, moving forward, then backward, then forward again, and saw something unpredictable, dangerous, violent. But Mars is not a god. It is a world. And what a world it is. Mars is about half the size of Earth. Its diameter is 4,212 miles. To put that in perspective, you could fit Mars inside Earth with room to spare. Its surface area is about 55 million square miles, roughly the same as all the continents of Earth combined. A whole world waiting. A whole world dead. But Mars was not always dead. Billions of years ago, Mars was a very different place. It had a thick atmosphere. It had oceans of liquid water. It had rivers, lakes, perhaps even seas. It had a magnetic field that protected it from the solar wind. It was, in many ways, a second Earth. We know this because we have seen the evidence. The rovers have photographed ancient riverbeds. Orbiters have mapped sedimentary rock, formed only in the presence of water. The Perseverance rover is currently exploring an ancient river delta, the place where a river once emptied into a lake. 4 billion years ago, water flowed on Mars. But then something changed. Mars is smaller than Earth. Its interior cooled faster. As the core cooled, its magnetic field weakened, then vanished. Without that field, the solar wind, a constant stream of charged particles from the sun, began stripping away the atmosphere. Over millions of years, the air thinned, the oceans evaporated, the water froze. What was once a blue-green world became the red desert we see today. The atmosphere that remains is a ghost. It is 95% carbon dioxide. There is almost no oxygen. The pressure at the surface is less than 1% of Earth's. Standing on Mars without a spacesuit, your blood would literally boil. Not from heat, from lack of pressure. The temperature on Mars averages minus 80 degrees Fahrenheit. In winter, at the poles, it can drop to minus 200. In summer, at the equator, it might reach a balmy 70 degrees for a few hours in the afternoon. Then the heat vanishes into the thin air. The surface is a desert of red dust and rock. The red color comes from iron oxide, rust. The entire planet is covered in rust. That is why it is red. That is why the Romans named it for war. The color of blood, the color of rust, the color of a world that has been dying for billions of years. But there are wonders here. The largest volcano in the solar system, Olympus Mons, rises 13 miles above the surrounding plains. That is nearly 3 times the height of Mount Everest. Its base is so wide that its slope is almost imperceptible. If you stood at its base, you would not see the summit. It would be hidden behind the curve of the planet. The longest canyon in the solar system, Valles Marineris, stretches across the planet for 2,500 miles. That is the distance from New York to Los Angeles. In some places, it is 4 miles deep. The Grand Canyon would fit comfortably inside one of its side valleys. There is water on Mars, frozen, locked in the polar ice caps, buried beneath the surface. The North Polar Cap is about 600 miles across. The South Polar Cap is smaller, but holds just as much ice. Combined, they contain enough water to cover the entire planet in a layer 100 feet deep. And beneath the surface, there is even more: permafrost, buried glaciers, aquifers frozen for eons. And there is dust. Fine, toxic dust that gets into everything. The dust is made of silicates, microscopic glass-like particles. It's sharp, it's abrasive, it's everywhere. Dust storms on Mars can cover the entire planet, blotting out the sun for weeks. The dust is so fine that it gets into machinery, into seals, into lungs. It's a constant enemy. This is Mars. A world of extremes, a world of lost oceans and frozen water, a world of towering volcanoes and bottomless canyons, a world that has been waiting for us for 4 billion years. And now we are finally ready to go. The journey to Mars begins on Earth, and it begins with a problem. The distance between Earth and Mars is not constant. The planets orbit the sun at different speeds. Sometimes they are close, sometimes they are far apart. When they are closest, at opposition, Mars is about 35 million miles away. When they are farthest, on opposite sides of the sun, it is nearly 250 million miles away. We will launch when they are close. The timing is critical. A launch window to Mars opens every 26 months when the planets align. Miss that window and you wait another 2 years. The first missions will launch in these windows. The first humans will launch in these windows. Even at their closest, the journey takes 6 to 8 months. 6 to 8 months in a spacecraft no bigger than a school bus. The International Space Station is the size of a football field. A Mars ship will be cramped. The crew will share space with equipment, supplies, experiments, each other. There will be no privacy. There will be no escape. Every sound, every smell, every movement will be shared. 6 to 8 months in microgravity. The human body did not evolve for weightlessness. In microgravity, bones lose density at a rate of 1 to 2% per month. Muscles atrophy. The sense of balance breaks. The heart weakens. Fluids shift upward, causing puffy faces and thin legs. Astronauts on the space station exercise 2 hours a day just to slow the decay. On the way to Mars, they will exercise more, perhaps 3 or 4 hours a day. 6 to 8 months of recycled air. Every breath you take has been breathed before. The carbon dioxide is scrubbed. The oxygen is replenished. But the air is never fresh. It smells of machinery, of plastic, of human bodies. The carbon dioxide scrubbers must work perfectly. If they fail, the crew suffocates in their own exhaled breath. 6 to 8 months of recycled water. Every drop of water on the ship has been used before. Urine is filtered. Sweat is reclaimed. The water you drink today was someone's sweat yesterday. The recycling systems must be flawless. There is no backup. 6 to 8 months of isolation. No fresh food, no open sky, no wind, no rain, no grass, just metal walls and the same faces, day after day after day. The crew will need to be carefully selected. They will need to be stable, cooperative, resilient. They will need to be able to handle conflict without violence, boredom without despair. But the real danger is not the boredom. The real danger is invisible. Beyond Earth's protective magnetic field, there is no shield against cosmic radiation. The sun constantly emits a stream of charged particles, the solar wind. When the sun flares, it releases bursts of radiation that can be lethal. A single solar flare could deliver a radiation dose that would kill an astronaut in hours if they were not protected. Cosmic rays are high-energy particles from distant stars, from supernovae, from the heart of the galaxy. They pass through matter like it is not there. They can damage DNA. They can cause cancer. They can kill. A spacecraft to Mars would be exposed to this radiation for the entire journey. The hull would absorb some, but not enough. The aluminum skin of a spaceship is not designed to stop high-energy particles. It is designed to hold air. For radiation, it is like tissue paper. Astronauts on a Mars mission would receive a radiation dose equivalent to a full-body CT scan every few days. By the time they reached Mars, their lifetime cancer risk would have increased by several percent. NASA's current limit for astronaut radiation exposure is based on a 3% increased risk of cancer. A Mars mission would push that limit. There are solutions. Water can shield radiation. The hydrogen atoms in water absorb particles effectively. If you wrap the crew compartment in a layer of water, you create a shield. But water is heavy. Heavy means more fuel. More fuel means more weight. More weight means more fuel. The rocket equation is unforgiving. Some designs propose using the ship's own wastewater as shielding. Others suggest using the fuel itself. Hydrogen is an excellent radiation shield. Still others talk about artificial magnetic fields, tiny bubbles of protection around the ship. Some engineers propose a storm shelter, a small, heavily shielded compartment where the crew can take refuge during solar flares. None of these have been tested in space. All of them are theoretical. They will need to be proven before humans can go. Then there is the problem of landing. Mars has an atmosphere, but it is thin. Too thin for parachutes alone to slow a heavy spacecraft. Too thick to ignore. It's the worst of both worlds. Entering the Martian atmosphere, a spacecraft experiences temperatures of over 2,000 degrees Fahrenheit. The heat shield must survive that. Then, at the right moment, the parachute deploys. But the atmosphere is so thin that the parachute alone cannot slow the craft enough. Engineers have solved this problem for rovers with the Sky Crane. The Curiosity and Perseverance rovers were lowered to the surface by a rocket-powered descent stage that hovered above the ground, gently setting them on cables. The Sky Crane worked perfectly for the rovers, but a human lander is 10 times heavier. The human lander will need a different approach.
Perhaps it will use larger parachutes. Perhaps it will use retro rockets from the beginning. Perhaps it will land like the Apollo lander, with a descent engine that slows the craft all the way to the surface. Every design has trade-offs. Every design has risks. There is also the question of landing site. You can't just land anywhere. You need a flat area, clear of rocks. You need a place with water ice beneath the surface. You need a place with enough sunlight for solar power. You need a place that is safe. The search for landing sites has already begun. Scientists have mapped the surface with orbiters. They have identified dozens of potential sites. They will narrow them down. They will send rovers to scout. They will choose the best. The journey is possible. It is being planned. But it is not safe. It will never be safe. It will be the most dangerous journey humans have ever attempted. And we have not even landed yet.
You have traveled 35 million miles. You have spent 8 months in a metal tube. You have survived radiation, isolation, the endless emptiness of space. Now you step onto the surface of Mars, and it tries to kill you. The air. The first thing you notice is that you cannot breathe. Mars's atmosphere is 95% carbon dioxide. There is almost no oxygen. A single breath would not kill you instantly, but it would be your last. You have seconds to get your helmet on. Even if you had oxygen, the pressure is wrong. At the surface of Mars, the atmospheric pressure is less than 1% of Earth's. Your blood would literally boil, not from heat, from lack of pressure. This is a condition called ebullition. Your bodily fluids would turn to vapor at body temperature. You would swell to twice your size. Within a minute, you would be dead. So you wear a pressure suit, a full body envelope of protection. It gives you air, it gives you pressure. It is your world. The suit is not just clothing. It is a miniature spacecraft with life support, communications, thermal control, radiation protection. It must be perfect. If it fails, you die. The cold. The temperature on Mars averages minus 80 degrees Fahrenheit. In the Martian winter at the poles, it can drop to minus 200. In summer, at the equator, it might reach 70 degrees. For a few hours in the afternoon. Then the heat vanishes into the thin air. Your suit has heaters. Your suit has insulation. But if your suit fails, you have minutes. At minus 80, exposed skin freezes in seconds. Frostbite turns to hypothermia, turns to death. The cold is not just uncomfortable, it is lethal. The temperature swings are brutal. During the day, the surface might warm enough to feel almost comfortable. At night, the temperature plummets. The difference between day and night on Mars can be 100 degrees or more. The expansion and contraction of materials can crack seals, break equipment, cause failures. The radiation. Back on Earth, we are protected by two shields, the atmosphere and the magnetic field. The atmosphere blocks cosmic rays, the magnetic field deflects the solar wind. Together, they make Earth a haven. Mars has neither. The atmosphere is too thin to block anything. The magnetic field is gone, long since frozen in the planet's crust. So the surface of Mars is bathed in radiation. A year on the surface of Mars exposes you to a radiation dose equivalent to about 15 full-body CT scans. It increases your lifetime cancer risk. It damages your DNA. It ages your cells. It is a slow killer, invisible, relentless. We can build habitats underground. We can cover them with Martian soil. We can use water as shielding. But every time you step outside, you are being irradiated. Every spacewalk is a calculated risk. Every hour on the surface adds to your dose. The dust. Mars is covered in dust. Fine, sharp, toxic dust. The dust is made of silicates, microscopic glass-like particles. It is sharp enough to scratch metal, to wear through seals, to damage equipment. The Apollo astronauts found that lunar dust was a nightmare. It got everywhere. It clogged the joints of their suits. It scratched their visors. It got into their lungs. They smelled it, tasted it, could not escape it. One astronaut said that lunar dust was the single biggest problem of the Apollo missions. Martian dust is worse. It contains perchlorates, chemical compounds that are toxic to humans. Perchlorates affect the thyroid gland. They disrupt hormone production. They are poisonous. They're also powerful oxidizers, meaning they can react violently with organic materials. If perchlorates get into the habitat, they could create a fire hazard. If you breathe in Martian dust, it could cause severe lung damage. If it gets into water supplies, it could poison your food. If it gets into your habitat, it is nearly impossible to remove. Every time you go outside, you bring dust back in. Every spacewalk means decontamination. Every entry into the habitat is a ritual of cleaning. The dust is a constant enemy, a slow poison, a reminder that Mars does not want you here. The gravity. Mars has about 38% of Earth's gravity, less than half. For a few days, it would feel wonderful. You could jump higher, you could carry heavy loads, you would feel light, free, strong. But over months and years, the low gravity would change your body. Your bones, no longer bearing your full weight, would lose density. Astronauts on the space station lose 1 to 2% of their bone mass per month. On Mars, it would be slower, but it would still happen. After a year, you might lose 5 to 10% of your bone density. After 3 years, you might not be able to walk on Earth without months of rehabilitation. Your muscles, no longer needed to fight gravity, would atrophy. Your heart, no longer pumping against gravity, would weaken. Your sense of balance, calibrated for Earth, would drift. You would feel dizzy. You would feel weak. You would feel like a stranger in your own body. When you return to Earth, if you returned, you would not be able to stand. You would not be able to walk. You would need months of rehabilitation to recover from what Mars did to your body. The isolation. Mars is a long way from home. At its closest, communication takes about 4 minutes one way. At its farthest, it takes about 24 minutes. There's no real-time conversation with Earth. There's no calling for help. When something goes wrong, you are on your own. The nearest other human is millions of miles away. The nearest hospital is a planet away. The nearest friend is a voice in a radio talking to you from the past. If someone has a heart attack, there is no emergency room. If someone breaks a leg, there is no surgeon. If someone goes mad, there is no psychiatrist. The psychological toll of Mars may be the hardest to overcome. Isolation, confinement, the constant knowledge that death is one broken seal away. The Mars missions will be the longest space missions in history. The first crew will spend 3 years away from Earth, 3 years with the same people. 3 years without seeing a tree, without feeling wind, without smelling rain. 3 years knowing that if something breaks, you fix it yourself. 3 years of being the most isolated humans in history. This is what Mars wants to do to you. And yet, we are going anyway. So, how do we do it? How do we take a planet that is actively trying to kill us and make it a home? The answer is technology, science, engineering, and a willingness to live differently. The habitat. Your home on Mars will not look like a house. It will look like a cave. The first habitats will be buried, covered in Martian soil. They will be protected from radiation, from temperature swings, from the dust. They will be pressurized. They will be warm. They will be safe. NASA has already designed these habitats. They are cylindrical modules launched on rockets, landed on the surface. They are connected by tunnels. They are covered with regolith, Martian soil for protection. Inside, they are bright, clean, efficient. They are home. Each module is about 30 feet in diameter and 40 feet long. Several modules will be connected to create a base. The first base will be small, perhaps the size of a large house. Later bases will be larger, with greenhouses, labs, workshops, living quarters. Later, we might build above ground. We might use Martian brick, compressed soil baked into building material. The soil on Mars contains iron oxide, which gives it its red color. If you heat it, it can be sintered into solid brick. No cement needed, no water needed, just heat and pressure.
We might use inflatable structures, covered with regolith for protection. These structures can be folded small for launch, then inflated to full size on Mars. Covered with a layer of Martian soil, they provide protection from radiation and temperature. They are lightweight, cheap, easy to deploy. We might even dig tunnels into the ancient lava tubes that snake beneath the surface, creating vast underground cities. The lava tubes of Mars are a wonder. They are formed when molten rock flows beneath the surface, leaving behind empty tunnels. Some are hundreds of feet wide, some are miles long. They are naturally shielded from radiation. They are protected from temperature swings. They could be the perfect place to build a city protected from the elements, a city safe from the dangers of the surface. The air. On Earth, we take air for granted. On Mars, you make it. The Martian atmosphere is 95% carbon dioxide. Using a process called electrolysis, you can split CO2 into carbon and oxygen. The oxygen you breathe. The carbon you store or use for other purposes. This technology already exists. NASA's MOXIE experiment on the Perseverance rover proved it works. MOXIE, the Mars Oxygen In Situ Resource Utilization Experiment, produced oxygen from Martian air, hour after hour, day after day. It proved that we can breathe on Mars. MOXIE was the size of a car battery. It produced oxygen at the rate of a small tree. Scale it up to the size of a refrigerator and you can supply a person. Scale it further and you can supply a whole habitat. Scale it further, and you can supply a whole colony. The same process that makes breathable air can fuel your return trip. The oxygen can be liquefied and used as rocket propellant. The carbon can be combined with hydrogen to make methane, another rocket fuel. The technology to make fuel on Mars is already being tested. The water. Mars has water, lots of it, locked in the polar caps, buried beneath the surface, frozen in permafrost. The North Polar Cap alone contains enough water to cover the entire planet in a layer 100 feet deep. Beneath the surface, there are glaciers of pure ice, covered by a thin layer of dust. Radar data from orbiters has revealed these glaciers. They are hundreds of feet thick. They are pure. They are waiting. You drill, you melt, you filter, you drink. Water is heavy to bring from Earth. It makes more sense to find it on Mars. Once you have water, you have drinking water, irrigation water, water for hygiene. You also have oxygen. Electrolysis can split water into hydrogen and oxygen, giving you breathable air and rocket fuel. The technology is proven. The water is there. We just need to find it, drill it, and use it. The first Mars missions will land near the poles, where water is accessible. Later missions will drill deeper, tap the aquifers, create a water infrastructure. The food. You cannot bring years of food from Earth. It is too heavy. You must grow it on Mars. The Martian soil is not soil. It is regolith, crushed rock, no organic matter, full of toxic perchlorates. But you can clean it. You can wash away the perchlorates. You can add nutrients. You can turn dead rock into living soil. The perchlorates are soluble in water. Wash the soil, collect the water, treat it to remove the perchlorates, and reuse it. The soil becomes safe. Greenhouses on Mars will be underground, protected from radiation, lit by LEDs. You will grow potatoes, wheat, soybeans. You will grow lettuce and tomatoes for fresh food. You will grow spirulina for protein. You will raise insects, perhaps for animal protein. The science is young, but it works. Earth-based experiments have shown that plants can grow in simulated Martian soil. The International Space Station has grown lettuce in microgravity. Scientists have grown potatoes in Mars-like conditions. With time and effort, Mars could feed its inhabitants. The power. Mars is cold and dark, but it has sunlight. Less than Earth, but enough. At the equator, the sun provides about 40% of the power it does on Earth. That is enough. Solar panels will provide power, lots of them, spread across the landscape. They will need to be cleaned constantly. The dust is a constant enemy, but they will work. The solar panels will be laid out in fields like farms. They will track the sun. They will generate electricity during the day, charging batteries for the night. For dust storms, for emergencies, you need backup. Nuclear power is the answer. Small reactors, compact and reliable, could provide baseline power when the sun is hidden. NASA is developing the kilopower reactor, a small, portable nuclear reactor that could power a Mars base. It is about the size of a refrigerator. It is safe, it is reliable, it is proven. 1 kilopower reactor could power a small base. Several could power a city. The suit. Your spacesuit is your second skin. It gives you air, it gives you pressure, it keeps you warm, it protects you from radiation. Future Mars suits will not be like the bulky suits worn on the moon. They will be sleek, flexible, designed for mobility. You will wear them for hours at a time, for days at a time. They will be your world when you leave the habitat. Scientists are working on suits that recycle air, that manage temperature, that filter dust. They are working on boots that grip the rocky surface, on gloves that let you handle tools, on helmets that give you a wide view of the red landscape. They are working on suits that you can put on quickly, without assistance, because on Mars, there may not be anyone to help. The suits will be custom fitted for each astronaut. They will be comfortable enough to wear for long periods. They will be tough enough to survive the harsh environment. When you step onto Mars, your suit is the only thing standing between you and death, so it must be perfect. The return. You have to get back. The plan for the first missions is to send the return vehicle ahead, unmanned. It lands on Mars, uses the atmosphere to make its own fuel, and waits. When the astronauts arrive, the fuel is ready. They launch, rendezvous with a waiting spacecraft, and come home. Later, we will build permanent bases. People will stay for years. Some may never come back. But for the first explorers, the return trip is planned from the beginning. They will not be stranded. They will not be abandoned. They will come home to Earth, changed forever, but alive.
So why go? Why risk all of this? Why spend billions of dollars and years of your life to live in a cave on a frozen desert planet? Because Mars is the next step. Human beings have always pushed outward, from Africa to Asia, from Asia to Europe, from Europe to the Americas. We crossed oceans in wooden ships. We crossed mountains on foot. We crossed deserts with nothing but hope. We walked on the moon. Mars is the next ocean, the next mountain, the next frontier. It is not about escaping Earth. It is about expanding human presence. It is about becoming a multiplanetary species. It is about ensuring that if something happens to Earth, an asteroid, a pandemic, a war, humanity survives. It is about science. Mars holds the secrets of the solar system. It may hold evidence of past life, fossils of creatures that lived billions of years ago when Mars was warm and wet. Understanding what happened to Mars could help us understand what could happen to Earth. Understanding how life began on Mars could help us understand how life began on Earth. It is about inspiration. When Apollo astronauts walked on the moon, they changed how we saw ourselves. They showed us what was possible. A human mission to Mars would do the same. It would inspire a generation to dream, to build, to reach. It is about us. We are curious. We are explorers. We are the species that looks at the night sky and wonders. We are the species that builds telescopes to see farther, that builds rockets to go higher, that builds dreams to reach the impossible. Mars is waiting. It has been waiting for 4 billion years. It was waiting when the first fish crawled onto land. It was waiting when the first humans looked up at the red star in the sky. It is waiting now. Now we are ready to go. There is a dream beyond survival. A dream of turning Mars into a second Earth. A dream of making the red planet green. It is called terraforming. The word comes from Latin, terra, meaning earth, and formare, meaning to shape. Terraforming means shaping a planet to be like Earth, making it warm, making it wet, making it breathable. On Mars, terraforming would require 3 things: heat, atmosphere, and water. The heat. Mars is cold. The average temperature is -80 degrees Fahrenheit. To make it warm enough for liquid water, we need to raise the temperature by about 100 degrees. How? By creating a greenhouse effect. On Earth, greenhouse gases trap heat, keeping the planet warm. On Mars, we could release greenhouse gases to do the same. One idea is to melt the polar ice caps.
The North Polar Cap alone contains enough frozen carbon dioxide to double the Martian atmosphere. If we could vaporize that CO2, the thicker atmosphere would trap heat, warming the planet. The warming would release more CO2 from the soil, which would trap more heat, which would release more CO2. A feedback loop, like the one that made Venus hell, but here it would make Mars more like Earth. How do we vaporize the ice caps? Some ideas: orbiting mirrors that focus sunlight on the poles, giant greenhouses over the poles, trapping heat. All of these are speculative. All would take centuries. The atmosphere. A warmer Mars would begin to release gases trapped in the soil: carbon dioxide, nitrogen, water vapor. Over centuries, the atmosphere would thicken. The pressure would rise. Eventually, the pressure might be high enough that humans could walk outside without pressure suits, though they would still need oxygen masks. But there is a problem. Mars has no magnetic field. Without that field, the solar wind will strip away any atmosphere we create. Slowly, over millions of years, the air we make will be lost to space. We would need to replenish it constantly, or find a way to create a magnetic field. Some scientists have proposed placing a magnetic shield at the L1 Lagrange point between Mars and the Sun. This shield would deflect the solar wind, protecting the Martian atmosphere. It is a huge engineering challenge, but it is theoretically possible. The water. A warmer Mars would have liquid water. The polar caps would melt. The permafrost would thaw. Rivers would flow. Lakes would form. Perhaps even oceans. The water would create clouds. The clouds would create rain. The rain would create weather. The weather would create climate. Mars would become a living world. The life. With warmth, with air, with water, we could introduce life. First, bacteria and algae to create oxygen and build soil, then mosses and lichens to cover the land, then grasses and shrubs to hold the soil, then trees to create forests. Over thousands of years, the red planet would turn green. The sky would turn from pink to blue. The air would become breathable. Mars would become a second Earth. The question: but should we do it? Should we change an entire planet to suit our needs? Mars is not a blank slate. It has its own history. It has its own geology, its own landscapes, its own potential for life. If there is life on Mars, microbes perhaps, buried deep beneath the surface, what right do we have to destroy their world? Some scientists argue that we should preserve Mars as it is, that we should study it, explore it, but not change it. Others argue that life is life, and that spreading life to a dead world is a moral imperative, that if we can make Mars green, we should. This debate will continue for centuries, but the first steps toward terraforming may happen sooner than we think. Not a full transformation, but the beginning of one. The first greenhouse gas factories, the first water extraction, the first plants growing in Martian soil. Mars is not a safe place. It will never be safe, but it could become a home.
So we return to the question we started with. Why cannot we survive on Mars? And how might we? We cannot survive because Mars is a world of extremes. No air, no pressure, lethal cold, deadly radiation, toxic dust, weakened gravity, endless isolation. Everything about Mars is trying to kill us. But we are not powerless. We will go in ships that protect us from the void. We will live in habitats buried beneath the surface. We will make our own air, our own water, our own food. We will wear suits that give us life. We will build cities that shelter us from the storm. We will survive because we have to, because the human spirit demands it, because Mars is there. The first human footsteps on Mars will happen in our lifetimes. A child born today may grow up to walk on the red planet. A teenager now may be among the first settlers. The future is not written, it is being built. Mars is not a safe place. It will never be safe, but it is a place, and we are going. The red planet waits. cold, silent, dead. But not for long. Sweet dreams, the journey is just beginning.